是这样啊，没错啊，干嘛我就是我们设定。全部都往这里跑。嗯。
拜一啊，OK OK，拜一哈，这个拜一，拜一啊，拜一哦，拜一晚上哦拜一晚上，OK 啊，哎，
可以吃。
早做不早教哦，
那早不早？
早做早教哦。Okay, before we begin with new stuff, so yesterday I cleaned up some detail in the proof. I, I've uploaded to the Moodle. So let's go back to the Alexander subbasis theorem. I think if you notice in some of the old topology textbook, they use base instead of basis. So whenever you see base or basis, they should be equivalent. Okay, but in our class we didn't use the word base. I think the reason why they changed to basis probably is the influence of linear algebra. Change to basis. Okay, right. Let's go back to this part here. So remember yesterday we proved this Alexander subspace theorem. Okay, maybe to test again. Okay, never mind. I wrote it down. So one direction is immediate. So from left to right is immediate, but right to left needs some advanced tool, which is the Zone's lemma. Okay, we use Zone's lemma in this proof here, and it argued to the end we prove that the collection of open cover that has no finite subcover should have a maximal element. Okay, should have a maximal element. And then we try to argue that this maximal element actually has a finite subcover. We actually have a finite subcover. How do we argue that? We first intersect it with a subbasis, okay, subbasis. And then we say that this intersection cannot cover X. Okay, if it can cover X, then by the assumption of open covering by subbases having finite subcover, it will form a finite subcover for A as well. Okay, so it doesn't cover X. Then we found this little x in the complement of this intersection here. And then we found that because we have a subbasis, right? So subbasis form what? It has a basis property here. So this x should lies inside a finite intersection of elements of subbasis. Okay. And I said that A union with any of these Si or Sj here is an open cover of X because A is already covering X. But the problem here is this Si is not in A. And if it's in A, then we cannot find this complement. So each of them is not in A. Okay, I think this is the problem that Ziqian confuses a bit. So yesterday I just claimed that it is an open cover that's greater than A. But why? Because this Sj is not in A. Okay, if it's in A, then A union Sj is just A. Okay, yeah. And then the other part that people confuse is, I think this notation I use here. Since A union Sj is larger than A, and A is the largest one without finite subcover. So A union Sj should have a finite subcover. So this is how I denote the finite subcover here. Okay, AI union Sj. But AI here I put a superscript J for it so that I know this set of finite subcover is work for A union Sj. Okay, for different J you have potentially have different finite subcover. And then what do? I take the intersection of this because everyone cover X, right? So everyone should contain X. So in particular, if I take the intersection, they still contain X. And then in the end, if you consider this kind of property here, so this kind of set inclusion, if you take intersection of two unions, what do? You can expand it up, right? You can expand it up. So if you take A union B intersect C union D, what do you get? And what do you get? Set theory. So you can think of it like the arithmetic, right? Opening the bracket. A plus B times C plus D. Okay. So, but what we care is the last intersection here. B intersect D. Whatever intersection before should lies inside this union here. Does it make sense or not? For example, A intersect C lie in this intersection or not? A intersect B lie inside this intersection. B intersect C lie inside the union or not? A union C. Okay, so we don't need to be so precise. So we wanted to live inside this cover here. But if living in this cover is good, why is it good? Because for the first term here is finite. For this term, I can simply use U to cover it. So altogether is a finite subcover. Yeah. Okay. Okay. Yeah. Okay. Right. So any question about yesterday proof? No. Any other question that you want to check? Okay, so what have we done yesterday? We proved the Tikhonov theorem, which is every product of compact set is compact. If an arbitrary product set is compact, then the factor are also compact. Okay. And then we introduce compactification. So what's the compactification is? It is a compact Hausdorff space. Okay, compact Hausdorff space. Hey, Hausdorff space is quite important. Do you think if space is not Hausdorff, can you put a matrix on it? Cannot. Why? Yes, we prove that matrix space has to be Hausdorff. The one line proof, right? What else we prove? A matrix space also has to be first countable. Remember? Okay, so if your space is not first countable, then there's no hope of going to a triangle. So these are a few criteria you can keep in mind. And not only this space is compact Hausdorff, it is the closure, okay, of your space. This is the closure of your space. Okay. Okay. Today we will continue discussing Stone-Cech compactification. Okay, we will continue discussing the Stone-Cech. Okay, so yesterday we tried to motivate this compactification using continuous function. Okay, so we will redo it again. So this is our motivation. So what's our motivation here is if, okay, y is a compactification of x. Okay, so you want to ask the question is under what condition can a continuous function or continuous real valued function, okay, we just consider map to real number, can be defined on x to be extended continuously to y. Okay, so what do you think? And what do you think? When can you extend a function, continuous function? And then it is continuous again. Okay, extend continuously. What do you think? Yes. What do you think? No ideas? Can you extend bounded function or not? Let me think how to motivate you guys. So let's look at maybe function like define on say open interval from 2 to 1, 1 to 2. Okay. Can I extend to the closed interval 1, 2, for example? Okay. So let's say my graph is a is a continuous graph loop like this. Is there any way to extend this continuous function from one open interval 1, 2 to closed interval 1, 2? How? You just fill in the limit point of this one, correct? Of course, you can extend it different way, right? But if you're going to do other way, what do you get? You get a not continuous function. Okay, but we want to do it continuously. Okay, we want to extend it such that it is still continuous. Okay. What do you mean? For example, in this case here, this function, if you extend to from open interval 1, 2 to close interval 1, 2, what's the difference between these two intervals? You are missing how many points? 2 points. So you just need to tell me at x equal to 1, what's the value of f? At x equal to 2, what is the value of f? That's all. Okay. Yeah. You just fill the term. Okay. Although this is for finitely many points. For infinitely many points, you need to tell me how do you fill them. Okay. Sometimes there's a nice way to fill them. Sometimes there's not. For example, what do I mean by nice way to fill them? For example, let's say I have a description on this curve here. So let's say what curve we want to take. Let's say we take x squared, fx equal to x squared. Okay. In this case here, if you want to fill this two limit point, what's the two limit point here? 1 and 4. Good. Okay. So you can fill it. You can fill it by saying that f is taking 1 when x equals to 1, when it is in the open interval 0 to 1, 1 to 2, then it is x squared, and then when it is at 2, it is 4. Or you can simply say that fx equals to x squared on the closed interval. So in this case, there's a natural way to extend it. Does it make sense? Okay. Because the point 1 and 2 also follow the formula. That's it. Follow the function that's defined on the open interval here. Okay. So actually, you can see that what we drawn here is actually bounded. Okay, bounded function. But even that bounded is not enough actually. Okay, bounded is not enough. Let me give you an example. Let me give you an example. For example, let's look at this compactification as S1. Okay, filling one dot. Okay, so when can you extend a bounded continuous function 0, 1? What do you think? When can you extend it? When can you extend it? What do you think? You have 0, 1, and then you have some function, but you want to connect the two endpoints of your domain together, right? And you want to define such that the function on it is continuous. So meaning what? So you need to have your limit going to 0 plus, okay, from the right hand side equals to the limit from the left side to 1 to be equal so that you can fill the top. Does it make sense? Sense or not? Does it make sense? So, well, I mean, you can think of it like this. So let's say I got 0, 1. Right? I got a function looks like this. Make sense? Okay. But we are going to bring our 0, 1 together. So you can think of it as our function like working at the top here. Okay. So if this two limit point is different, then it is not continuous because at because every point you can only have one. You can only have one f value. So whether you want to put here, whether you want to put here, is not continuous. Only when their limit is the same, then you can extend the function continuously. Does it make sense? Any question? Question? I see some confused face. Yeah, I mean, you can imagine that you bend this real line, right? You bend this R2 into a cylinder. Can you imagine? Imagine this R2 as a plane, right? And then I want to join 0 and 1 together. So you can imagine this plane, you fold it, become a cylinder. So what happened to your function? Your function live on the cylinder. Can you imagine or not? Hello? Can you imagine? Okay. So you want to extend such that the function is continuous. Why do we want to paste? So this is our problem here compared to this problem. If y is a compactification of x, under what condition can a continuous real valued function defined of x can be extended to y? So here why we join them, because compactification of x, one of them is x1. This is a one way to compactify the open interval. So yeah. Okay. Does it make sense? No question? Any question? Yeah.
What is the limit equals
F0, but F0 doesn't have point, right? No point there. Of course not, because in compactification, the extra point is infinity. We gave an extra point there. It's not 0, it's not 1. It's an extra point. You know how we join these two lines together? We add an extra point here. We call it infinity. If the limit from the right left exists, only I can define this F infinity here. And then I define it to be this two limit here. Does it make sense? Make sense? This part is a first year calculus actually. How do you define a continuous function? Left and right have to approach the same limit and then take the same point there. So here, this point is the infinity point. So the difference between now and what you learn in calculus is our domain become curved, no longer like Euclidean. I mean R2, Rn. It's still in R. Yeah. Can be put into Euclidean, by the way. Yeah. Okay or no? Make sense? Okay. All right. Then the other case is easier. For example, if we want to consider the 2-point compactification, is exactly what you said just now. If you can extend it, if and only if the limit to the right of x and the limit to the left of f exists. As long as it exists, we just fill it in. Just now, this is what we did just now, right? As long as it exists, then I just fill it in. Okay. If it is a 2-point compactification. Okay. And the last thing that we left yesterday is actually the compactification that we get from compactification we get from the topological cycle. Okay. So yesterday I said that this compactification helped us to extend the map fx equals to sine 1 over x on 0. Okay. This compactification helped us to extend this map on the domain 0, 1. Okay. Yeah, this is what we left yesterday. Okay. Now. Oh, by the way, yesterday actually I have a typo in my slide. This when I talk about this example, right? You still remember? I said that this two is homeomorphic. Remember, this one is closed. So here somewhere should be closed as well. So we can close at 0. And let's close at 0. Okay. Yeah, this is not an embedding for open interval 0, but a half open interval. Okay. Yeah. This is slightly different. Okay. Right. So from these examples, right? From this example, what you can see is we look at a different bounded continuous function on 0, 1. Okay, and then we look at a different compactification, and then we ask whether the continuous function, okay, that defined on 0, 1 can be extended or not. Okay, and then you can see that from this extendable case, right, we are looking at different kind of compactification. Okay, we have 1-point compactification, 2-point compactification, and then there's a topology sine curve compactification. Okay, so there are a few ways to compactify it. Okay, and so which compactification is good? Huh? 2-point. Why is it? Why so? 没有，又没有了。怎么会没有？随便讲，哎，不用随便讲话。社会已经够乱了，不要再随便讲话。要随便讲话，用脑子可以吗？Okay, yeah, right. So I mean, yeah. So actually, we don't pick. Okay, so we want a theorem. We want to base. Okay, that is so that y have the property that every bounded continuous function extend uniquely. Okay, we want every bounded continuous function to extend uniquely. Okay, to a continuous map. Okay, we want to do it for all bounded continuous function. Okay 吗？So 我们没有要做选择，我们全部都要 extendable 在这个 space 上面。Okay, when is it true? Okay, when is it true? So when do you have this kind of compactification? If and only if your space started with is completely regular. Okay, we will prove this. So let's prove this. So one direction is easy. Actually, we discussed the other day. Which direction? So whenever you see if and only if you can play a game, which direction is easy? One criteria you can check is whenever you want some construction should be involved. So construction part should be tedious. 没有人敢乱讲话了，现在。To prove, okay. Prove the other one. So you mean from right to left is easier? Okay, unfortunately, that one is the hard part. Okay, so the easier one is from left to right. Okay, why? You are a space living in a compact Hausdorff space. A compact Hausdorff space is normal. Okay, you need to remember. And then a normal space, what can you do with it? You can use a recent lemma. Okay, you can separate points and close set. Then that means your space is completely regular. And then completely regular is hereditary. Every subspace of a complete regular is complete regular. Okay, so this is the flow. Okay, actually I discussed yesterday already. It's in the note. Okay. Okay, so this one actually we discussed. Okay, discussed yesterday. So the hard part actually is the other way. Okay, you need to construct the space and then prove all these property here. Right. Do you know how many things you need to do in the right statement here? Do you know how many things you need to do? How many things you need to do here? Let's discuss what the things you need to do, then we will do it. First, what do you need to do? You need to define your y first. But to define this y, I need to check a lot of things, right? What things you need to check? Compare Hausdorff, and then first S closure is 1. And then next thing, what do you need to do? Every bounded continuous map extend uniquely to a continuous map. This sentence got two things you need to do, you know. What's the two things you need to do? Yes, existence and uniqueness. So they are quite involved here, this sentence here. Existence and uniqueness. 可以吗？身为数学家，要把这个句子拆掉，拆完你要知道自己要做。OK 吗？这个如果人家问学数学来做么，算确实是没有用，你要懂把人家的话拆成这样，你才有用。它里面的话藏了什么东西，你知道吗？明白吗？OK 了。Okay, so there are how many things you need to do? About like 1, 2, 3, 4, 5, 6, quite a lot of things. Okay. So we break into it step by step. Okay, we break into this sentence step by step. So first, we only have one property to start with. 没有很复杂的. We only know X is completely regular. Okay, from this one thing, we can prove this many things. Does it make sense? Okay, from this one thing, we need to build all this machinery up. Right. So how should we build our Y then? So the first step is to build Y. Okay. Build Y here. Okay, so how do we build it? So so we have discussed. So the example we see yesterday was we compactify 0, 1 open interval 0, 1 using the topology sine curve. But when we do that compactification, what do we consider there? We consider a graph. Okay. How do we obtain this graph? It is from a bounded continuous function. What is that bounded continuous function? Sine 1 over x. Okay. So in this case here, we do the same. Okay, we do the same. So let's denote BC be the collection of continuous bounded. Okay, actually bounded continuous sound nicer. Real value function. From x to y. Okay. Right. So what can we do here? Okay. So what we can do here is for each f in this space here, there exists a closed bounded if such that fx is living in f. Is this true? If you have a bounded continuous function, you evaluate it at every point. Okay, it should be living in some closed interval because it's bounded. So what can we do here? So here is the magic. So here is the magic point here. What we will do is, what we will do is we will consider all possible f. We will consider all possible. So I don't know how big is the f. Okay? So it's an arbitrary product of every f in this bounded continuous space here. This if here. Okay. This if here is in term living in what space? Maybe let us study this space a bit. So this space actually live in an arbitrary product of and then what's the definition of arbitrary product? Function. Remember, it's a function. Every element here is a function from the index set to the union of this factor. Okay. Remember or not? Exam question. This is equals to the function from the index set to the union of factor. Can everyone understand this notation? R to the sum set. Sum a to the power set b is a function from b to a. Okay, but what is this? Actually, BC, this BC form a vector space. Okay, this is, I think, really the dual of BC. Okay, actually, we are looking at the dual of BC. Hey, where's my star? The dual of BC. Okay, dual of a vector space. Okay, no? Does it make sense? Okay. Okay, a dual of a BC. You guys took advanced linear algebra, right? Okay. So in this case here, what happened? So we can consider. So now we consider an evaluation function. Okay, evaluate function from h. Sorry, yes, let's call it. Let's call it h then. Call it h. from X to this product. Okay. What's the natural way to do this? What do you think? What's the natural way to do this? I give you a point. Okay, how to go into this space here? What's the natural way to do it? What's the natural way to do it? What's the natural way to do it? How do you define this IF? IF contain what? Image of X under all function, right? So what can we do here? You have a point. I say this is evaluation, right? So what you can do? Yeah, you just take all the F and then evaluate it. This is a point in this product space. Does it make sense? Make sense or not? Okay. So the claim here, so what do we do here? We take a space, we just make it into number. Not just one number, multiple number. Where do you get this multiple number from? All the bounded continuous function on your X. So meaning what? Meaning what here? Meaning what? I use bounded continuous function to view this point X. I don't know how to view X, but I can use bounded continuous function to see this X, and then see it in different way. Does it make sense? So one point here become a multiple views on this point. Okay, and then later we will provide compactification of this product space. So how do we provide compactification here? So I use H here, right? So this is suggesting this H should be a embedding. Okay. So it is actually a lemma that E is an embedding of X into a compact Hausdorff space. Okay, compact Hausdorff space. In particular, namely this arbitrary product of IF. Why is it compact? Because this is by Tikhonov theorem. Okay. And why is it Hausdorff? Because Hausdorff is productive. Yeah. Oh yes, thank you. Because I forgot to change here. Okay. So what do we do? So this lemma, I think we won't prove here. We will put into lecture notes. So this one, skip proof, quite technical here, skip proof. So what can we do is we can simply just define Y to be the closure of this embedding. Okay, closure of this embedding. Yeah. Okay. Does it make sense? Does it make sense? So this embedding of taking closure of embedding is what we use for how we produce a compactification last time, the lemma we proved yesterday. Okay. So this kind of why this give a compactification, this is what we have proven yesterday. Okay, this is what we have proven yesterday. Is this this one. Okay, this is the lemma we use. Okay, compactification induced by the embedding. But this embedding is special. I embed into an arbitrary product of IF. Where do I get the IF from? I get from the image of bounded continuous function. Does it make sense? Okay. 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 Then what time is it? Okay, we still have time to finish up. Let's finish out this proof then. So what's the next thing we need to do? The next thing we need to do. Step 2, we need to show that every bounded continuous map extend uniquely to a continuous map or into R. Okay, so we need to prove this. So there are two parts, right? We need to prove existence, we need to prove uniqueness. Okay. So is it clear how to prove? Is it clear how to prove? So you need to always keep an example in your mind, right? Yesterday, that example, the 0, 1 that get compactified to the topology cycle. Okay. Yesterday, how do I explain that? We provide an extension there. How do we provide extension there? So maybe let's go back to this example. Easier to motivate. How do we provide extension here? What do we consider there? We consider Y as the closure of who? Not just fx, right? The graph. Okay, the graph. Because if fx, then no limit on one side, so you cannot close it. That's the problem we met in MA1. But in topology, we look at the graph, put the interval in. Okay, so actually we look at x, fx. Okay, and then we take the closure. Okay, and then what do we do? We can just what? Just map it to the second coordinate. Just map it to the second coordinate. Okay, so sending what? Sending xy to y. Okay, then this will give the function sine 1 over x. So what have we gone through here? Actually, we've gone through an embedding here. Remember yesterday how I described y and y naught is different or not? X and S naught. X and the embedding of X. 还记得吗？啊，昨天金宝还跟我拍 story 放去 IG 了，是不是？怎样分辨 X 跟 X naught？ 啊 ，X is a topological space by itself. X naught 呢？ X naught is what? It's an embedding into a what space? What kind of space you embed it in? What's the space that the lemma need? Compact hostile space. It's how it sits in the other space. Because we are going to compactify there. Does it make sense? Why we can compactify there? Because that space is compact hostile. My limit point there. You yourself is no hope. You need help from the other. In that space, you can find a limit point. Okay. If yourself, you can have a lot of possibility, right? Just now we have one point compactification, 2-point compactification, topologies, sine curve compactification. So you have a lot of possibility. But if you put into a certain compatible term, it is quite clear what you have to get. So different Z might give you different compactification. Make sense? Okay, no. Okay. Okay. So in general, it's the same. So in general, it's the same. If you consider here, you replace with arbitrary product. What do? You just map it to the IF that the F you want to extend. That's all. Okay. Does it make sense? For general product. And for general product, you just project it into the IF that you want to extend. For general case. Does it make sense? Got question or not? Question? So this one is for the extend as distant part. So basically, you just compose the embedding with the projection map and project to the part that you want to extend. And uniqueness is left-hand exercise then. Okay. Okay. Any question about this theorem here? Any question? Which one? Which one? For a new case, for general case. General case. General case. General case. Okay. Sure. So, again, let's write it down in formally. What we do is there exists an embedding H from Y into the space here. Okay, so this embedding is exactly that sending write this down. So such that Hy is exactly equal to Hy. That is okay. This embedding is this sending Y to this X bar. Okay, and then so let G to be the projection map from this arbitrary product of IF to IG. So this is the projection map for function G. Okay. Then we will say that then the continuous map IG with H, composed with H, is a map from Y to IG. Okay. So this is the desire. So this is the desire extension for G. Okay. Why? Why is it that? How do you say it is an extension on G? How do you say it is an extension of G? If you restrict the space to just X, what does pi GH have to do on X? It has to be equal to GX. Okay, so why is it equal to GX then? So you need to ask, what is pi G capital H on X? Okay, so this embedding here, you should do Hx equals to little Hx. On X itself is just Hx. Okay, so capital Hx on X should be little Hx. Okay. But what is Hx here? What is the H, the embedding that we gave just now? Is the or the arbitrary evaluation on X. So I just pick out the G component. Yeah, I just pick out the G component. Yeah, it's literally the same. It's literally the same. Good. Any question? Yes, so for uniqueness, is a quite standard argument, so I think we just skip it. It's inside my notes. You can have a read. Or you want to go through together? Because I don't want to write it up. Maybe I can read through, and let you see. Okay, let me show you. Okay, I have it here. I don't want to write because it's quite standard. Let's. So why is it unique? So let's say if you have two extensions, okay, if you have two extensions, say there's point that they don't agree. Okay, call it X. Because they're different, so that if they agree, then no point, right? Okay, so suppose they don't agree. If they don't agree, find two open sets that contain these 2 points. Okay, such that their intersection is empty. And then what do you do? What you do is you can look at the open set around X, the pre-image of this point. This is X here. Okay, this 2 point here. Because G is continuous, right? So you can find this V such that G of V is in U and G prime of V is in U prime. I think it's not G of V. This one is G also. They have the same. They should have the same extension of the same function. Let me repeat. So, okay, this one should be just G. Okay, but our Y is what? Is a compactification of either you are limit point, either you are point in X. Okay, so what? So if you look at this intersection here, it should have some point in X. Because if X is the limit point, meaning every neighborhood should contain some point in X. So this intersection here should be non-empty. Some point in X. But if you have a some point in X, what happens? This is an extension of G. So they should evaluate to the same point. Okay, here shouldn't be a F. Here should be a G. They should evaluate to the same value. Okay, at this point here. But this contradicts that we pick U and U prime as empty. Okay. Why we can pick empty? Because it is a Hausdorff space. Okay, so there's a contradiction. So we use the limit point condition to contradict the Hausdorff condition through the extension of a function. Okay, now, so there's a contradiction here. So it has to be unique. Can follow? Follow? Yeah, you can look into more detail. Okay, any question so far? So far? Okay, no. Actually, a corollary here is a topological space is completely regular if and only if it is a subspace of a compact Hausdorff space. Okay, it's a subspace of a compact Hausdorff space. It's not just a subspace, right? It is a dense subspace. S bar equals 1 bar. Okay, actually, it's a dense subspace. Okay, so this is a corollary. A topological space is completely regular if and only if it is a subspace of a compact Hausdorff space. Okay, so this is the corollary. Okay. Yeah. So actually, there's one lemma I didn't prove, right? That lemma actually is quite technical. It's to prove that H is an embedding. Now you imagine you map into this arbitrary product. How is it an embedding? Why is it injective? Why is it continuous? why is it a homeomorphism onto the image? You need to check all this. Yeah, it's quite technical, so I leave it in my proof. Okay, let's break until 12:10, and then we will talk more about the Stone-Cech property. Okay, property of Stone-Cech compactification.那这是什么？就是我们面先讲，就是你是不是我们觉得懂，我就觉得懂，这边就走，这个是。这种跟什么是？对，剩下的会吗？for 这个 cost 还是 for different？ 这 cost 已经，这 cost 是停在 complete matrix 这一块。如果你去看我的 cost info， 它只停在 complete matrix 这一块。然后很大部分的东西，不懂啊，我上过课没有上，就是那些已经是比较专进去了，比较难去来读其他的。比如说那天我们 discuss 什么 parameter 啊，什么 locally find 这些，就还有一大部分的可以要做，对。在这个对开开另外一个对吧？还有比这更重要的课要上讲。这个现在只说这个没说过啊，这个应该三房的这个我是好像我觉得differential geometry 你是看 differential geometry geometry 你是看 algebraic equation， 当然也是 differential geometry， 所以 algebraic geometry 里面的东西属于，它是会用 algebraic 的方法去杀你，所以就不用再讨论 atlas 了，我直接有了。你把那个写出来，比如说 y 的对，还是在讲这个特别是没有，那边是看的是对，那边看什么啊？对 zero set study 那个 zero set 哦，怎么 study 法？有看到人家模拟位。有一个东西叫做李白色，我忘记讲模拟位了。李白色叫什么？你会觉得有点像那个 number theory 里面的李白色啊，就是可以除啊，怎么样？现在来做一个 promotion。因为我到现在搞不懂，就是我没有number theory 用，这边number theory 肯定 number theory 的。这两个跟 algebra 那还有什么差别 ？algebra 如果 algebra number theory 你可以想象成是用 algebra AA2 的东西去解，就是高啊。 problem 的 fundamental problem 不太一样啊，他们的出发点不太一样，但是可能可以收到同一个东西了，出发点不一样。然后 algebra number theory 的话是，你可以想象是去用 A 读的东西去记我们 theory 的东西，比如说什么呢？比如说 extension、g a l o extension 啊，你讲慢慢一步一步把号码加进来，都是从 Q 开始，可能 Q 过后 extend 另外一个 algebra number 这样，慢慢 extend。
然后讲 algebra 不是讲 A 的
用 A 的工具，用 extension 的工具，然后我们会杀敌 map between 这些 extension。
那 algebra 的问题是
我觉得 topology 难就是难，但是呀难就是难，每个有自己的难度，也有好玩的地方。肯定难肯定是去不了的，那就是看他多好了。
完全的让我下次讲，那我不用考这件事。MA 还是
瑞人是其实，我想一下啊，哦对啊，瑞人是其实不是很难，但是到了刚确的也是出片子。瑞人是因为最难，为什么瑞人是会没有那么难？因为难的部分已经在 MA 出现了。最难就是你那边看很多表达，等你那个过渡期过了，或者就会很长的蜜月期。蜜月期过了呢，你就要进发生那件事。发生的是为什么又难？因为又有 algebra 的东西。为什么 algebra 东西难？因为人往往会忽略掉 structure。比如说啊，你生活中在马来西亚生活，你跟规则到马来西亚真正我去出来，怎么会有？因为很少人去想背后的东西，但他们就觉得难，因为他们只是跟不出来。这就跟我每次跟我班的学生讲，你就是不懂什么叫算术跟数学，你做的在算数吧，你可以知道懂 Q，你还在算的，他不算不算，知道那种，这就分辨了大概分 Q 的。但是 of course 啦，你 apply math 的人，当然他们也是会有懂 pure math 的。我的理解就不是 pure math，他摆明就 apply math 小的，他也是叫我们做啊。但是如果你不 on apply side，他 more towards 他要你去算一些结果，因为他要那个结果，等有结果了，我们才可以讨论他的 principle。但是我 pure math 也是这样子的，你知道吗？有时候你去想啊，你去想一个理论出来啊，其实各种理论都可以问，但是你要什么就是哦，你要什么就取决于你想查你的 phenomenon 是什么，连你的 theory 才可以放进来的。你的 theory 可能可以问，但是不问我这个 phenomenon，能问我另外一个。所以你看，同一个 S1 来，我们用了几种方式来写，topology 的方式来，可能 differential geometry 也可以写，而 geometry 也可以写。而且从同个率也可以写啊，讨论东西不一样。但是很美的地方是，三方有时候他们讨论出来的 property 可以是活在同一个里面，又可以拎回来。比如说刚才我们study这个 S1 的时候，我没有告诉你它怎么连在一起的，我只是说丢一点对吧？那个 embedding 会告诉你什但是在 algebra topology，我们会告诉你说，哦，我有一条线，一条线一定有尾端，那我就把这两个尾端起来。这样的东西看一下，我看一下，其实你们的 note 大概已经写完了，其实 maybe 可能有机会的话，可能讲一点 promotion to complementary to tree， 告诉你们它有什么好玩的东西。planning 是这样的，这是 planning。OK， 我有一个 general 答案图这个东西 ，general 答案 ，OK， 管你什么好的不好，反正你就是不好的。这样讲，因为你不会啊，你怎么会好嘞？对吧？什么叫做好？我不知道，你反正就是不会的。OK， 你都讲你不好才 A， 所以说至少你有 D。OK， 所以我们 set 的这个 rule， 我觉得我是 set 在应该拿过 Algebra 1， 应该就可以拿。Group theory 过后就可以拿。我想这样想。OK， 我还没有讨论，我去跟他讨论，跟彼得讨论。对于难的东西，你要有一个正确的心态去读它。你不要想说我要靠一些什么小聪明啊，还是什么这样去学它，这是不对的。你学一样东西的话，你要去找它的真知识，真知识不能用小聪明来找。你一定要去做，多做，OK， 多看。当然，如果你比较巧的话，你是比较容易 get 到了，讲啊。但是这个东西不持久，我这样跟你讲，我这样跟你讲老实话，不持久。所以你会听到很多人说：“哎呀，我读一半，我以前很会，我然后觉得很难，我就抛弃数学。”就是这个咯，因为他不是真正要去学这个人，你明白吗？也有很多人抛弃，但是他绝对不是因为这个原因抛弃。他可能说：“哦，我要去做其他东西啊，我觉得数学，我觉得学够了。”这才是正确的方式抛弃数学。不正确的方式抛弃数学是，我觉得哇太难，我 reach 不到了。这个心态放在哪一个岗位都是错的。你在哪一个岗位都会遇到你碰不到的东西 unreachable。以后走进社会你就懂了。哎，那时候你要做梦，你放弃没？放弃咯，你就会看到很多那种狗屁店阿北啊。
接手给你一压轻松。
耶耶耶耶耶！
如果你学东西，你学轻松话，代表你不是学。
In some sense 啊，in some sense。Of course， 我理解。当然你要比如说我也有这样的心态嘛，就是说，比如说我第4年的最后一个 sem， 我也没有去拿那种很难的课，因为我也是要准备 TC， 所以这个东西你自己要平衡哦，但是不要贪便宜。我跟你讲，不要贪便宜，贪便宜这东西很危险，你贪得了一次，可能贪不了第2次，所以我们要脚踏实地做人。OK， 所以你说不好不用紧，只要你肯学，肯定学得会的。我都已经给你example了，我班有从20分考到100分，肯定做得到的。你要不要呢？如果你要这样讲的话，其实也 minimal 啦，minimal 算 minimal，你可能有应该有呀。如果你要你个的问法，我觉得对，我觉得 OK 呀。我没有用到高的话，theory 还没有进到那个，进到那个的话，我们可能要进到 category of shift， 那个比较难的东西了。technical 是这个 mentally 是我刚才讲的东西啊。OK， 2个都要兼顾。很多老师是没有管 mental 这个东西啊。思想准备很重要，其实你做对的思想准备，你就成功一半了。其实思想准备不对你就一直碰壁，一直碰壁了。OK 了，不要担心，不要担心。成绩不好不要担心。我比较担心的是你不要读吧，我这是最担心的。成绩不好肯学了 OK， 所以那种聪明不肯学那种，我不觉得他是什么好学生。
是一个好学生。人家好学生是学生，你为什么叫你学生？你要学呀、你才叫学生。你不学，你哪里是学生？你来翘脚啊，你来享受啊，不是？学是你的工作，不是摆烂。可以休息，我没有叫你不可以休息，休息一下可以，但是还是要回来学。好，在那边玩第一个东西，在这里。OK 了，没有啦，I mean，我做的东西，我觉得是好玩的东西啊，我才会去做。啊，对啊，哪一个东西啊？
你的那个跟那个1、2、3有不同的加起来吗？
继续讲，我忘记了，什么叫第二？
或者说没有你的朋友对你做的两个没有上出来，他们觉得要大声一点。
哦，也，那是我老师给的题目，然后后来要讲算，讲算的，那边我们用到的东西是 module，上次跟你讲过了，但是我们不只单看一个 module 嘛，我们是看 chain of，就是 module 之间会有 map，之间会有 map，然后它会分成 degree 哦，就是说你在哪一个，因为你可以排了嘛，有箭头嘛，连两个箭头 compose 起来，我们要让它等于0，这个东西叫做 chain complex。And then，就是我可以拿 chain complex 跟两个 chain complex 给它乘在一起，然后拿到另外一个 chain complex。但是呢，我在我的那个算法里面是，它乘了过后不是，它剩下的东西啊，变成很简单的 module，其实就是一个 field 罢了。什么 field 呢？我们那边用的是，那你想象成是 R 或者 Z。OK，it's not field 啦，it's module。OK module Z 很简单的 Z，就剩一大堆的 Z 在不同的 degree 里面，然后我就算它 dimension，这个 degree 里面有多少 Z 剩下来，这个 degree 有多少 Z 剩下来，然后就可以 form 那个 Jones polynomial，因为 Jones polynomial 发生什么事情，有一个 coefficient 乘那些什么 t 的 power 嘛，对不对？t 的那些 power 不是会告诉你它在哪一个 degree 里面，然后那个 coefficient 告诉你有几粒 Z 在里面。就是那些号码就被一个 space 代表，被几个 space 代表，然后那个 variable 就被位置代表。
然后就想一个是
对，是 T 罢了，T 告诉你哪个 degree，不同的 power 告诉你不同的 degree，不同的格，然后前面的那个号码告诉你有几个 Z 的存在在那个 degree 里面。这东西我们叫 categorification 啊，有兴趣不是下个 Sem 我会给那个 talk。可能我可以讲这些东西，and then 可能我再拎去 algebra geometry 哦。如果我们下个礼拜开，下个 Sam 开这个课的话，那个 talk 可能是一个这里的，这里的 department 跟那个中国 department join 的一个 seminar，then 有一个 slot 是我的，所以我可以讲这些，我可以讲可能我这个 PhD 最后做的东西跟怎样 link 去 algebra geometry。Okay, let's start. Right. Oh, okay, good. So we have this theorem here, right? This kind of special configuration here such that every bounded continuous method can be extended uniquely This kind of compactification is what we define as a Stone-Cech compactification. Okay, so this special compactification here we call it a Stone-Cech compactification. So one property is this is unique. So theorem the Stone-Cech. My C put at the wrong space and my head put at the wrong space. Put on the C, not put on the E. So Stone-Cech compactification beta x of a completely regular space is unique. Okay, so here unique should be take up to homeomorphism. Okay, let's think about how to prove this. How to prove this. I'll say this is a very standard proof. This is a very standard proof for algebra. Uniqueness up to homeomorphism. Because our space has a universal property here. Actually, this is a universal property. Okay, how do we draw out this property here? You can draw it out as a commutative diagram. Okay, so how do you draw it out? So let's start the proof a bit. So for every continuous f from x to r, okay, what can you do? There exists a unique g from dx to r, okay, such that when you restrict to x, you get f. Restrict to x, you get f. So this is a commutative diagram. Okay, you can draw here. Okay, so uniqueness can be drawn by this universal property here. So what is a good choice to pick here? Okay, what is a good choice to pick here? Since this works for every f, what is the good choice you can pick here? Yeah. Check. What's the definition? Yeah. Okay, good. Yeah, try and think about it. How you put this property together. Huh? Are we, seems like we are missing something here. Let me check. Seems like we are missing something. Let me check. Are we missing something here? It's like we are missing something. Let me check. So, I mean, okay. So we want to prove uniqueness, right? Where can we start? Of course, we need to start with two possible configuration of X, and then show that there's a homeomorphism between them. So one thing you can see is obviously there's an inclusion map from X to Yi and X to Y2. And the inclusion map is continuous. Ah, I see. We are missing one theorem here. That's why you don't know. So let's add this theorem in. So we only know that we can extend it to real valid function. Okay, but actually we have this theorem here. So theorem given any continuous map from X to let's say any compact Hausdorff space, then this F expand uniquely to continuous map G. So this, how do you imagine this word here? Okay, I know people, how to say, people scared of reading words. Okay, so you need to turn this word into a diagram. Okay, so how do you turn this word into a diagram? First, you have a continuous map from S to Z, and then it extends to a map from Y to C. Okay, but what's this extension means? Meaning, if you include X into Y, G on X is just F. So you have this diagram here. Okay, but what else? This G is special, you know. This G is unique. Okay, so given one F here, you will have a unique G here. So you use this diagram to remember this word here. Okay or not? Okay. So let's not prove this. Let's take this as granted first. Okay. So this Y, Y, I think Y I need to put it as what is this Y? I didn't tell you what is Y. So Y is the compactification of Stone-Cech compactification of X. So this special G here is only packing with this BX. Okay, packing with this. Does it make sense? Is it making more sense now? Okay. Okay. So any map out from X, if you have a Stone-Cech compactification, you can extend uniquely. So what is the content between this and the usual definition of Stone-Cech compactification? we change R to any compact Hausdorff space. Okay, if it's Stone-Cech, then this is R. Okay, but if you can make it to R, you can make it to any compact Hausdorff space. Okay, so this is the theorem here. Okay, okay, now I think we have better tools here. So you see, we have X include to Y1. Okay, we have X include to Y2. Okay. But what is Y1 and Y2? Stone-Cech configuration of XOR, correct or not? So meaning what? For this I1, there exists a unique G1. From where? If from Y1, then it's super boring. It's the same, almost the same map, identity map. Okay. So you can take Y2. Correct or not? Okay, such that you have this unique G1 extension. For the other one, you can take Y1 instead. Okay. The previous theorem. Okay. Okay. So what can you do next? You want to talk about maps between Y1 and Y2, right? So there's natural map between these two. There's a natural map between these two, which is what? G1 and G2 here. Okay. So if we consider what? If you consider, say, G1 compose G2, this is a map from where to where? Y1 to Y1. Okay, good. But this has what property? Such that what? G1 on G2 evaluated at X, you get. So, okay, because it's just inclusion. Okay. So, it is identity on X. There's an obvious map from Y1 to Y1 that does this. Identity map. Obviously, identity map from Y1 to Y1 is an extension of the identity map from X to X. Okay, so, but the extension is unique. Okay, so the extension is unique. Since extension is unique, G1, composed from G2 should be identity or not. Okay or not? Okay. And the other way is true also. Similarly, G2 on G1 is identity on Y2. Okay. So they are inverse of each other. Okay. Inverse of each other. Why is it homeomorphism? Why inverse is continuous? For example, G2 inverse, why is it continuous? Yes, because G2 inverse is G1. G1 is continuous. So. Okay, so it's a homeomorphism. Yeah, so there's just this theorem that we miss out. I think we need to add it in. So why we can change the R to arbitrary compact Hausdorff space? Huh? Say again.
Yeah, Stone-Cech compactification unit.
You mean that one is from the embedding, huh? By the configuration of embedding, is it? Otherwise, where is the uniqueness? So we prove uniqueness, we only prove existence. We use the embedding to find the configuration. We haven't proved uniqueness yet. Are you claiming that we use the uniqueness from the closure of the embedding? This is what you claim? Because we have proved this lemma here. Are you referring to this? Yes. Yeah. Okay. But remember how we prove the embedding? Sorry, how we prove the space that have that property? We construct a specific embedding. So through this specific embedding, it is unique. But what if you have other embedding that give you the same property, the Stone-Cech property? Can you imagine? Why cannot? Can I imagine? Because you pick a specific embedding just now. We pick a specific embedding. What if you have another embedding that gave you this potentially different space, but still having the unique extension property? Does this two space have to be the same? You get what I mean? Just now we use a very specific embedding. We consider the product. Let's say you use different embedding, also produce a Stone-Cech configuration, meaning you have the unique extension. Should they be the same space or not? Does that make sense? This one is specific for one embedding. That embedding should give you the same unique. So if you change embedding but still have Stone-Cech unique extension property, should the two space have to be the same? So the theorem here proves that it have to be same up to homogeneous. Does it make sense? Okay. Question? No question. No. Question. Difference of what? This one is specific for H. Specific. Just now that one is proving what? Compactification, the special configuration, as long as you satisfy the unique extension property. This one is pair with H. Just now one is pair with uniqueness extension. This is the difference. Do you see the difference or not? Why are they different? One is on the function. One is on the embedding. A lot of function happening here. If you say function, what function? One is the embedding of the original space. The other is the extension property, based on extension property. Maybe you can build your Stone-Cech configuration using different way. No need to use my embedding. But as long as you can produce a space such that it is compact Hausdorff, such that there's a unique extension property. Stone-Cech configuration, you no need to use my way to do it. You don't need to use the infinite product way. But if you use different way, are they the same or not? My theorem says they have to be the same up to homeomorphism. Okay or not? Does it make sense? Okay. Question? Question? No? Okay, so this uniqueness is paired with the embedding. You fix one embedding. So that's why this word induced by the embedding. 每一个字都很重要。OK， 不要 ignore。虽然你要会看重点，但是对来 对我们来说，每一个字都是重点。数学已经是一个很简化的语言了，其实，所以每一粒字都是重点。我们要放上去的字都是重点，不是重点的字可以丢掉。OK，每一个都是重点。啊，不然的话，我直接放 Compactification 就好，怎么要摆这个？对呀，所以很重要，这个 Compactification 是 pair with 一个 embedding 的 fix 了，你看 fix 了 ，suppose fix 了这个 embedding 已经被 fix 住了。如果你放一个 H2 啊，又不一样了。Okay， 对吗？我们不是有 example 呢 ？Open interval 0 1，different embedding give you a different configuration， 对不对？怎么可能 x1 可能吗 ？Is S1 homeomorphic to close interval 0 1? One is connected, the other is not connected. Eh, still connected. Okay, let me ask you a question. Is S1 homeomorphic to 0 1? S1 homeomorphic to close interval 0 1. Is it? So no. Yes. Can you give me the homeomorphism? What is the homeomorphism? Yes, I mean, can you give me the function? Maybe from 0 1 to the other side. What's the homeomorphism that you can give? Huh? The usual cosine. Cosine 2 pi x sine pi x. But I think this is not quadratic, right? 0 and 1 sent to the same point, right? So, is there a chance to modify it? These two are compact, right? And these two are connected, right? Then these two cannot use to show the homeomorphy already. Well, any idea? Send to empty set. Why send to empty? I mean, empty set is not an element on both sides. So, and empty set not in here. There is also not in here. Any chance to get them homeomorphic? Seems like not, but I on top of my head now. Any idea? No, so why no? Cardinality wise, I think you cannot do it. You cannot, that also cannot. The two main chapter we study cannot use. Why is it not compact? Why is it not homeomorphic? Need to do long construction. How's the construction? Okay, try and search for this. And I want to comment the last thing that we left yesterday actually. I try and find the Stone configuration for 01. It turns out that quite complicated a little bit. Okay. So if you want to study what's the Stone-Cech configuration of 01, maybe you can ask, is it S1 or not? Is it the closed interval 01 or not? Because those are a candidate for compactification, right? So if let's say it is x1, right? So let's look at this bounded continuous function. Okay, do you recognize this bounded continuous function here? So this is the CDF of a standard normal distribution. Okay, it is bounded continuous. But if your configuration is a circle, then the left and right limit should be the same. Okay, but one side you go to 1, the other side go to 0. So you cannot join the two together. Okay. So we try to extend what? Where did you learn this? Probability theory or statistic? Probability theory. Okay, so try one if we can compactify your space or not. Okay, can extend your continuous function or not. Okay, cannot extend. Okay, if too compact space. How about the 2-point compactification? Is it possible or not? Okay, for this case, we know that it's not possible already. This is from the MA1 case. If you consider the sine 1 over x. Remember, if we want to add in the limit point, we actually need to add in the whole interval. You cannot just add in points, 2 points. So what should it be? Okay, so what should it be? So if it exists, we can consider this simple function here, sin x. Sin x is obviously bounded and continuous. Okay, if you look at this map here, and you look at some pre-image, okay, pre-image at every point. Okay, pre-image at every point. In particular, for example, A0, you can see that it is a discrete point. Okay, it is discrete point. Okay, n pi is a discrete point. And similarly, you can look at the pre-image of this extension on the Stone-Cech compactification. And look at these two, compare the two inverse image. Because you know that the extension, when it restricts to x, is just AT here. It's just the original map. Okay, so you compare these two maps here. So obviously AT is in BT, okay, because BT got more points. And then you can note that actually AT is discrete because these are n pi's. Okay, they are discrete. For example, A0. For all the other points, the same because periodic. Okay, it's periodic. But it is not discrete in SC, because this Stone-Cech compactification space is compact. Compact in so it is a being infinite subspace in a compact set. Okay. So do we have this implication? Compact implies limit point compact. Good. Okay. Then meaning what? Meaning this space is not discrete anymore in that space because it is an infinite set. Okay. And what else? What else is BT minus AT should be non-empty. It should be non-empty. For every T should be non-empty. Okay. But you see, how many T inside this region here? Uncountable. So you at least already add uncountable point into your original space. Okay, at least. So actually, how big is this configuration to this 01? How big actually? Actually, you can prove that it is 2 to the power c. So meaning it is as big as the power set of R. Okay, as big as the power set of R. Okay. Not that I put R here because I make a homeomorphism between 01 to R. Okay. Because we want to discuss interesting example of function just now. Okay, so you can prove this a bit involved actually. So I didn't found new reference actually. These are all reference, right? Or 70, 89. I think maybe it's quite complicated, so people don't want to put into their notes. So you can look for this. But what can you say about this cardinality here? This space is 2 to the power uncountably many. Okay, so what space is this? So in the same old reference here, Anger King, they prove that the cardinality of every first countable compact Hausdorff space is at most countable. So if you put first countable, if you put compact, if you put Hausdorff together, this set can be at most uncountable only. But the Stone-Cech configuration here is much larger than uncountable. Okay, so meaning that it cannot be first countable because we know that it is compact Hausdorff. So it cannot be first countable. Another thing is, so where is it not first countable? Actually interesting here. Because we know that R is first countable. So where this point is not first countable is the point that we added in. So when we try to compactify this space, this new point become not first countable. Okay. So since this space is not first countable, this Stone-Cech configuration actually is not metrizable because we know that if you can put matrix on the topology, it must be Hausdorff, it must be first countable. It's not first countable, cannot put matrix. Not a matrix space. It's not a matrix space. Okay. But I haven't found what is the exact space, but I'm not sure if anyone identified it with some useful space. Okay. We just know that it has a Stone-Cech configuration that can do the unique extension property for us. But I haven't found what's the actual space. Okay. Okay. Any question before we break? Then I think last week we were left for Azella Ascoli for the whole week. The super theorem, huh? I think for the whole week. If we finish earlier, then we finish earlier. Yeah, the whole week. Because we will do 2 versions. One is a classical one, and then one is a general one. General one, I think we will go it quite briefly. Otherwise, quite involved, a bit involved from the dimension. For classical one, I think we will do it a bit slower. I want you to appreciate it. The classical one in the R case, and then later we'll move to general topology. General topology. Then we will finish this course. Okay, so this is the road to end general topology. Okay, any question or you want to have question on your assignment?